good morning. Let's start. I will go to the last part of this course and or the last session for this course, covering mostly the two last parts. I have a little bit of leftover from part 3, and I'm running a little bit behind my self-defined schedule. Okay. Perfect. Okay, now it's turned on. Thank you. So I will go a little bit quicker through this numerical methods for computing open loop optimal controls. This is quite standard and classical anyway, so you will find that in many books. And I will then try to have a bit more time for the last two parts of new material. Okay. Yeah. Why is that not working? Because I must have to click inside. Yeah. So the core challenge is here. Now we want to compute a control function that depends only on time, right? So we have a certain initial time and the final time we want to compute that function. And there are essentially two ways. So one is the two main options that we have. One is to use what I showed you before, use the Pontryagin minimum or maximum principle, then you get necessary optimality conditions. You may recall there were certain differential equations, there was an algebraic condition that some term is 0, and there were boundary conditions for x at the initial time and for lambda at the final time. I will write them down in a minute again. And then what we try is we try to set up a numerical scheme that tries to solve the necessary optimality condition differential equations by discretization in time, maintaining all the algebraic and boundary constraints. This is what is called an indirect solution method. The other option is we just take the optimal control problem as it is, discretize everything. We discretize the ODEs, we discretize the integral that is in the performance criterion, and then what we get is a finite dimensional nonlinear optimization problem after discretization, so-called NLP. And then we solve this NLP just by picking a suitable optimization algorithm from what is available. There are very good algorithms available, IPOpt, for example, usually in connection with Casadi, which does computes all the gradients that you need automatically. That's a very good thing. This is what you call a direct solution method. And there's also another phrase, or two other phrases for these two methods. You would usually call this first optimize then discretize, because you first solve like abstractly the optimal control problem and then you discretize. Well, this is called first discretize and optimize. You first discretize to get a finite dimensional problem and then use an optimization algorithm. Now we'll quickly go through the main idea how to do the method on both sides and what are the advantages and disadvantages. So let's go for methods based on the maximum or minimum principle, the so-called indirect solution method. So this first optimize and discretize. This is the model problem I want to look at. Just for, I think this doesn't need, I think this is the typo here. It shouldn't be it doesn't need to be the continuous functions. If you use the Pontryagin principle, we can do with measurable functions anyway. But this is the structure of the problem. So we have a Lagrange term, we have a Meyer term, we have the differential equation, we have some terminal condition here, and we have this initial condition there. And then the necessary conditions of optimality are the following, as I said, two differential equations, an algebraic equation here. And then we have initial conditions and terminal conditions, right? We have a terminal condition here, an initial condition here, and a terminal condition here. And this makes it a boundary value problem. So you may know that if you want to solve an ordinary differential equation, just based on the initial condition, compute the solution for the next time. That's numerically really easy. But if you have parts of the variable fixed here and the other part fixed here, then it gets very difficult, because then there's no single shot method that would compute this thing, right? So this is the difficulty. There's a boundary value problem contained. That's the main difficulty really here. And the idea is to split the conditions into two parts and then solve iteratively. So we have parts of the conditions will be, so the scheme will be such that parts of the conditions hold at each iteration, while others are not. satisfied at the beginning, but only after the method proceeds and we produce iteratively better and better solutions, they will be satisfied with less and less defect, right? And so what we solve for, what we always maintain is just by solving it numerically. We solve this differential equation numerically, we solve that one. We include this algebraic equation here, and we include the initial condition. And all conditions which are terminal conditions, so we have a TF here at the end of the horizon, this is the one that we will only satisfy after a while during the iteration. So that's the idea. So, and the idea is very simple. We solve numerically this one with some initial guess, lambda 0k. K is the iteration counter here, lambda 0k. And then we compute the defect here. So this is like, all this should be 0, right? If we have converged, we compute the defect, and if this defect is small enough, below a certain accuracy, then we stop the algorithm. If not, then we use some update of lambda 0k and also new k, which is actually not present here. This would be the, okay, this is the Lagrange multiplier for the terminal condition here. So it's there to enforce that this goes to 0. Yeah, what could we do there? Well, it's essentially a root finding problem for this quantity here, right? And for root finding problems, the fastest numerical method is Newton's method. So that's something one usually uses here, some variant of Newton's method. So we want that this at k tends to infinity tends to 0, so that we can stop after a certain number of iterations with sufficient accuracy. And Newton's method will work. So what we do is we do this Newton step here, so we compute some kind of search direction. This is, you get this by solving a system of linear equations, which is written here, right? So this is the search direction, and then you update, or the update direction, and you update by adding precisely this delta lambda and delta mu to lambda 0 and mu. That's the classical Newton method as you find it in textbooks, just adapted to this kind of problem. And this works very nicely. So here's an example. This is the one that we have seen before. The only thing I'm changing here is now initial and terminal condition. I have them free here. And for the particular choice of initial condition equal -1, terminal condition 0.75, if we initialize this Newton scheme with this initial guess for the new 0, this is the Lagrange multiplier for this terminal condition, and this is and lambda 0, that's the initial condition for the Lagrange multiplier for the this is lambda 0 in the maximum principle. Then this is the solution that you get. So this is the x star, the optimal solution, going from -1 as it should, right here at time 0 to 0.75 at time 1. This is the optimal adjoint lambda star, and this is the optimal control, which is actually, well, up to numerical errors, I would say constant. It just looks varying here, but if you look at the numbers here, if you can read them, they only change in the fourth digit after, no, actually, no, sorry, not even the fourth, in the seventh digit after the decimal point. So here you see them more clearly. What you see here are the iterates. So blue is the first guess, then K is after 50, red is after 50 iterations, yellow after 100 iterations, and purple after 151 iterations, and the final solution here was computed after 188 conditions, and the terminal conditions that were meant, so this was like, so accuracy was about 10 to the -3 here for the here you see how these defects evolve and how they tend to 0 here. Okay, yeah, a little remark. I didn't want to say more, and particularly I haven't said much about how we solve differential equations numerically. I will say a little bit more about that when we talk about the direct methods, because there we have to do the same. Okay, but just a little remark, some remarks. So these indirect methods, you first have to compute the necessary optimality conditions from the maximum or minimum principle to set up the system of differential equations. But that's kind of mechanic, right? So you can really do it with a recipe. That's not really difficult. It's very easy to include input constraints. We didn't have them in the example I showed you, but to incorporate them would be quite easy. And the advantage of these indirect methods is that they are often very precise, so you can really get much more accuracy than the 10 to the -3 that we have if you are willing to wait a little longer. They are also quite memory efficient. There's no need to store something like large matrices or anything. So they are really, really good from that effect. But there are two main disadvantages. The first thing is if we have state constraints and if they become active, then the necessary conditions of optimality become much more difficult and also much more difficult to solve. So you really have to massage the system and try to see whether your numerical solutions really satisfy these conditions. So it's really much more difficult to apply if you have state constraints. And if you have unstable dynamics, so if you, for a fixed U, the solution would depend very sensitively on the initial condition, right? So then you get numerical issues, because this would really make the Newton method or any other method you want to apply difficult to converge. You need a very good initial guess, so something which is already quite close to the true optimal solution. And this requires manual attention, so you have to play around with initial conditions to find the right one. I remember that I did this as a student, so computing optimal trajectories, and the hardest task was really to find a good initial guess. Once that was done, it worked nicely, but finding a good initial guess is really the difficult part. Yes, that was a question.
Maybe you're saying here, why you call it indirect?
It's indirect because, well, indirect is that we first set up the optimality conditions and then discretize the problem. So it's first optimized, then discretized. This is what is called indirect. And direct would be the other way around. I will come to that in a minute. Yeah, so these two reasons, these two properties here, this is a bit what could cause us problems, and which is why, for example, in model predictive control, which I will talk about in the next part, this is often not the method of choice. Yeah, you could say, okay, if the dynamics are not unstable, there is no problem, but it happens that usually either the adjoint dynamics or the state dynamics, so one of the two equations, is unstable because they are kind of opposite to each other in a way. So one of the other will be unstable, so you can't really help. Okay, yeah, now let's have a quick look at direct solution methods. As I said, the idea is we do not set up any optimality conditions, but what we do is we just take the problem as it is, this minimization, this differential equations, and these constraints, and convert this into a nonlinear optimization problem, finite dimensional one. So where psi is now a finite dimensional vector of dimension n psi. Right, so that's the idea, and this one should somehow approximate that one. That's the idea. So if we solve the NLP with some numerical NLP solver, we get an approximate solution to that one. And yeah, in order to do that, we have to think about, well, there are two aspects of the discretization. We have to discretize the space of control functions, and we have to discretize the differential equation. These are the two steps that we need to do. Because this is optimization in the function space, while this is optimization in a finite dimensional vector space. We have to go from one to the other in a meaningful way. And you can go very deep into that and do a lot of analysis. I'm just sketching the idea here. So, as I said, how to discretize U, how to obtain a solution. Okay, yeah, the idea is that's the classical numerical analysis idea. If we're looking for some unknown function, we approximate it by some, well, a linear combination of finitely many basis functions, right? And look for a solution in this reduced space that is spanned by all functions of this form. Right, so basis functions phi k, and the question is which basis functions to use, and there are, well, different authors have different opinions. I'm just showing you a couple of possibilities. So the simplest and I think most widely used are piecewise constant basis functions, so the green ones, right? So you have certain intervals. This is actually this is a typo. This should be T1. So this is not TF. TF is right. This is typo. Anyway, but so these are the discretization steps, right? So piecewise constant would be that. Then you could have piecewise linear requiring continuity. I used that on Tuesday for the optimal value function, right? This was the picture that I had, but here is for the control function. You could use piecewise linear without continuity, which if I were asked, I would always prefer over that, because we know that there might be jumps required for getting optimal control. So enforcing continuity of the control function by using this ansatz function is, I don't think, a good idea, but some authors do that. And you could, of course, use also something higher order, like a piecewise cubic here with continuity, and you could also do that without continuity, of course. So there are lots of different ways, and you can write all of them in this form, as I have it up here, like this form where phi k has just to be chosen the right way. Okay, yeah, so as I said, piecewise constant is, I guess, the most widely used choice. So the simplest and the most widely used. Also because if you really have a real-world system, it's easy to implement, right? You just keep your control input constant on small time intervals and change it from one time interval to the other. Yeah, and the second is how to discretize, how to solve the differential equations. I will just discuss fixed step size integration methods. We have a fixed step size called h here, which is the difference between two consecutive time instants here. And then we write down some g's of discrete time dynamics which map the previous state and the control that is active here at this time interval to the state at the next time step. And the simplest choice, I already mentioned that when we discussed the Hamilton-Jacobi-Bellman equation, would be the Euler scheme. So G is just x plus h f t x u. But more sophisticated schemes like point, Vesicle, Kutta, implicit methods may be advantages. I'm not going into detail here. So there are many, many other choices that are better because they have a better order of convergence, better approximation properties, or in case of implicit methods, better stability properties. So there are many good reasons not to use Euler, but this would be the simplest you could do. Okay, yeah, so if we do this with this optimal control problem, I'm just putting here some abstract h of p to be able to capture different kinds of terminal conditions that we would like to have. Then what we do is we have two methods now to apply what I said. So we could write it in the following way. So let's have a look at now only this Meyer term here. We know that we can always convert the Lagrange term into a Meyer term. So this is without loss of generality. And then what we do is we replace the differential equation by this difference equation where we have this, sorry, this should be T0, we have this terminal condition here. And we replace the constraints by constraints that are now only active at this discrete time points, right? And capital N is the number of the discrete time points that we have. So what does this mean? Well, this means that somehow by doing this iteration here, we compute in one shot from the initial condition, which is somehow the initial condition is, wait a second, there's something wrong here. X of t naught is h of p. Yeah, it should be t naught here, right? From this initial condition, we compute by iterating this in one shot the x of n, and then we minimize over that, right? So this is in one shot, and this is why it's called a single shooting method. So we really compute iteratively, but without anything in between, just by iterating this numerical solution method. We compute the state xn, on which then the optimization criterion depends in this one shot. And the ODE is here approximately satisfied for all iterates because we use this numerical approximation scheme. The method is very easy to code. The constraints are enforced at the discretization points only. That can be an issue because there might be problems where this is not enough, where you also would like in between 2 points to have constraint satisfied. Number of decision variables is a very important thing, which would be here like, so the important thing is how does it depend on the dimension, and the dimension here is this NU is most important, and of course the number of steps that you do. The trouble with this is, if we go back to the system, if we have this initial condition here, and if we change this initial condition a little bit, and the dynamics is unstable, then the solution will change a lot. And we have the same problem, as I said before, for the indirect method. If we Now it's not the Newton method, it's some optimization solver, but also the optimization solver will have a real difficulty solving the problem if we have a very sensitive dependence on the initial condition, because internally it will do similar things like this shooting, this Newton method that we had before. There's fortunately a remedy for that, and this is the last thing I would like to mention here. The remedy here is what is called multiple shooting. And in multiple shooting, what we do is we add additional optimization variables. So before we only had the U, right, the components of the control as decision variables. Now we have additional decision variables, which we call psi0 to psi n-1. And what we do is we solve the differential equation not in one shot, iteratively from beginning to end, but we split the solution into n steps. So we always start from psi of k, and from psi of k we compute x of k plus 1. And then, of course, we would like to have that x of k is the same as psi of k in the end, but we don't enforce this just by setting this, but we enforce this as a boundary condition, as an additional condition on the optimization variables. And this means that if we change the initial condition, then only the first equation here will change immediately. And this instability is broken up into many pieces. And the additional cost is, of course, that we have more variables and that the optimizer needs to make sure that in the end this is satisfied. But it only needs to be satisfied in the end. So we, rather than enforcing that the differential equation is satisfied for all steps from the very beginning during all iterations of the optimization, now it will only be satisfied in the end, because only in the end this constraint will hold, right? So here is an application for that. It's this optimal investment problem that we had before that I showed you, and you see that this also works very nicely then with this multiple shooting method, and there are very good implementations that you can get online, and if you want to play around with that, it's really something that you do not need to code yourself, but where you can find very good tools online. Okay, yeah, so let me skip the comments here because they are maybe just say that this multiple shooting is really the method of choice for unstable systems. It's much better than single shooting, and it's the method of choice. This direct method with multiple shooting is the method of choice, for example, in model predictive control. And the reason is that it's very, very reliable, right? So in contrast to the indirect methods where you have to tune by hand, find the good initial conditions, if you want to run this automatically, right, and do not want to think about how to initialize, how to do things, the direct methods are much better. They require more memory. They are not as accurate in the end, but they are usually accurate enough for real-world applications. Okay, there are other direct methods where you can parameterize with piecewise polynomials, where you can use orthogonal polynomial approximation, which is called pseudospectral methods, where you can combine these above, do it with multiple shooting, and so on. And what's the good thing about these is if you want constraint satisfaction not only in the discretization points but also in the pieces in between, then these methods are usually better. So this is one of the advantages there. Yes.
Okay. Just go back to slides. You are running the algorithm in back of that, the one before. Yeah, in reverse time or in direct time?
No, forward.
Forward time.
Well, actually, time somehow vanishes if we pass this to an optimization solver. The optimization solver wouldn't think about time, just about certain variables that are coupled, right?
Yeah, my question comes because I see h is 0 equal to h of p. H is not kind of final.
Sorry, H is this artificial initial condition, which unfortunately has the same name as the discretization parameter. This is a different H. So
this, what does tell us this condition H?
H says, well, H is just a condition that is because that's just a placeholder for various types of conditions that you might want to use. So
yeah, that's infinite, even a finite time, not even initial, right?
that's true.
That's so, where I asked
that's right.
Reverse time or forward time.
That's right. There is no final condition here. Maybe you should have also a final condition.
But or maybe it's an x of tf equals
x of t. That's what I think. Maybe that it's you should have x of t0 and x of tf. You should have
x t0. Why? X t0 where you start, so it's fixed by your condition.
Right. But I should write it down. I should write it down. You're right. This is maybe a little bit too inconcrete. So it could be final and terminal conditions, but it's not written that way. So this is not okay. But anyway, so if this is after discretization, this is passed to a nonlinear programming solver. And what they would do is they don't care about time. They just care about conditions and how things are connected. And that's what they would do. So it's not really an issue then, but you have to make sure that your problem is solvable, of course. So let's see. Thank you. This is, I have to rework these parts. Okay, there are other direct methods. And there's a very nice website where you can look at what kind of optimization software would be good for which kind of problem. So this is really, I had a look at that recently and I found that very helpful. And there's also this very nice lecture notes by Benoit Chachouard, which I mentioned before, where you have this, which really gives a lot of practical hints if you really want to do this numerically and solve it. Okay, let me summarize this part 3. So I talked about numerical solution methods. We had the dynamic programming on Wednesday and the open loop today. So dynamic programming gives us an optimal feedback law, while this indirect and direct methods, they give us open loop optimal trajectories. The numerical effort of dynamic programming grows very, very fast with the state dimension, much faster than that of direct or indirect methods. Deep reinforcement learning may provide a remedy here. I talked about that, but it's not yet clear for which kind of problems you could really do better with that. So I will come to that in the last part today. And indirect methods, they are more accurate, but also slower and particularly more complicated to handle than direct methods. So whenever you want things to work reliable and automatically, direct methods are often the method of choice. And multiple shooting is much better for unstable problems than single shooting. Okay, conclusion so far. There is a class of problems which is really, if you talk to control engineers, which is really their preferred way of formulating practical tasks. And these are usually high-dimensional optimal feedback control problems. High-dimensional comes automatically. If you have complex applications, you would have a lot of states. And feedback is important because there's always uncertainty, there are always disturbances, model errors, whatever, and you need feedback to compensate for that. And none of the classical techniques are really suitable for that. So the dynamic programming in the classical form is not possible to do for high-dimensional systems. Indirect methods are possible to apply to high-dimensional systems, but they don't give you a feedback. So what to do? I would like to present, and this is also very much connected to my own research, would like to present you 2 techniques that overcome this limitation, not for general optimal control problems, but for optimal control problems that have particular properties. I don't think you can expect that you can do this for any optimal control problem you can think of. You need to exploit structural properties at that point to get beyond these limitations here. Okay, and this is part 4, model predictive control. This is one of the methods that does precisely what I just explained. So what is model predictive control? It's an approximate solution method for infinite horizon optimal feedback control, which does not rely on dynamic programming. So it does not use dynamic programming, rather it uses open loop optimal control, usually direct methods. I said that we need structural properties, and I would like to explain to you the so-called turnpike property. And that's the crucial structural property that enables model predictive control to yield near optimal solutions. And then I will, in the end, presenting a challenging industrial use case where I was involved in solving that, where we really applied this to a true industrial problem, not academic, but really something that runs in practice in several places in Europe. Okay, model predictive control. This is the outline of this part. I will first introduce the method itself, then I will talk about the turnback property. I will present you main performance result, and I will then present you this use case, which is about optimal startup of combined cycle power plant. Okay, what's model predictive control? Maybe you have seen that before. What does forget the first line? That's from I should have deleted that. So what does model predictive control do? We want to solve an infinite horizon problem, and I'm using here the discrete time formulation because that's the usual way that you find in model predictive control. And you would like to approximate that by the iterative solution of finite horizon problems. Because the finite horizon problem, right, this is something that you can solve with direct methods very quickly and very efficiently. Particularly if n is small, right? This is what you would like to. If n becomes very large, then you have lots of decision variables, a long time horizon, that's difficult again. But if n is relatively small, then you can really solve this in milliseconds. So you remember this pendulum swing up I showed you. That was model predictive control, and the time for solving one of these problems was 50 milliseconds there. And that worked on a standard laptop already 5 years ago when we did this. So this is really something you can do quickly. Yeah, and we want a feedback law. So how do we get a feedback law if we do it this way? And the point here is the feedback law is obtained implicitly by solving this over and over again with new initial conditions. And I think it's most easily explained with a picture. So what we have is we have a certain initial condition here, x naught, and then we solve an open loop optimization problem on a finite horizon. Here it's 5 steps, so 4 steps, 1, 2, 3, 4 steps. And this is what is called the prediction in predictive control. This is what the P stands for. And then what we do is we follow this solution for one step. And then we come to a certain point x1. If our model was accurate, then we get exactly here. If we had perturbations, we may end up near, but not exactly there. And then what we do is we measure this point x1, and then we solve again the optimal control problem on a finite horizon, but now on a shifted horizon. Again, 4 steps into the future, so we solve from here to that. And we will get something which is maybe somehow similar, but not usually identical to what we had before. And then we follow the new solution for one step. We optimize, we get a new one, we measure that, we optimize again, we follow that, we optimize again. And so we get two things during this procedure, through this procedure. One thing is that we can generate arbitrary long solutions, so infinite horizon solutions, if you like, from finite horizon solutions by always taking the first pieces. And the second is we have a feedback mechanism, because if we optimize, we look at what is the current value, we measure the current value, and we plug that into the optimal control problem. So the optimal control problem can really see if there was a deviation from the previous plan and correct that. Right? So the feedback control value here is not a map that we store in some data structure, but it's actually an algorithm that's evaluated online as the first element of the finite horizon optimal control sequence. Right? So that's the idea of model predictive control. An online generation of a feedback by optimizing fast enough. And the question is now, how does that work? Right? So in principle, there's absolutely no reason why plugging together the first elements of finite horizon optimal control sequence should give us something good, right? Good in the sense of a performance criterion. So when can this be good? Well, I guess a necessary condition for this being good is that if we have a horizon that is sufficiently long, and the solution must be somehow similar to the infinite horizon solution, right? If the finite horizon and the infinite horizon solution were completely different, you can't expect that this works. And this brings me to the turnback property, because that's a property that guarantees precisely that. It is really the thing that we can use. It's kind of redundancy property, so the optimal control problem has a certain redundancy, and this is what we can use. Okay, so the turnpike property, I will describe it here for the problems that we solve in each step, so these finite horizon problems. We have a cost function, we have state and input constraints here, and the informal description of the turnpike property would be the following. It says that any optimal trajectory stays near an equilibrium, which we call xe here most of the time. And that's basically the simplest way of simplest form of the turnpike property. There are much more complicated ones, but this is the one I would like to use here. Okay, why should that be the case? I would like to illustrate this with two simple examples. And the first example is, both examples are really very simple, one-dimensional, discrete time, linear dynamics. So here what we have is the following. So the dynamics is x plus, so x at the next time is 2x plus u. So what's happening here, if we don't have a u, if we set u equal to 0, and the state doubles each time. If we start with 1, we get 1, 2, 4, 8, and so on. So it immediately diverges very quickly, exponentially fast to infinity or to minus infinity, unless we have very particular form. But what we want is we have the state constraint here. We would like the state to remain in this interval minus 2, 2. So the control has to act, right? It has to do something. And this, of course, creates some cost. And this is the cost that we measure. So our state cost that we sum up in the problem is just u squared. So the idea is we would like to keep the state of the system in this interval, minimizing the quadratic control effort. That's the idea. And yeah, have a look at this a little bit, and then you maybe can answer this one. What would be the state where you would like to stay, to be, so that it is really cheap? So what's the cheapest state for keeping the system inside X? Let me write down the dynamics once more. Here is chalk, so that you can see that. So it was like x, let me write it like that, x t plus 1 is equal to 2 times x t plus u of t, and the cost that we want to minimize just depended on u here and was u squared. So what's the cheapest state for keeping the system inside? So I have three options.
Sorry, is it correct the question, which is the cheapest state, or
yeah, the cheapest state? Where would so you can I'm asking you, yeah, the cheapest state. So the control has to do something, right? And the question is, where is it? What is the cheapest place? So if you start at say x equal to 2. I mean, yeah, it's so cheapest in the sense that you start at a certain point at this, say, consider this as initial condition, and you run the system, and you would like to find the state where the cost is minimal. Of course, to keep the system inside. Well, if you have no idea, then maybe you can just guess what might be the right answer. Yeah, you can please scan, and then we'll see what the majority thinks. Okay, who needs more time to think? So let's see whether someone answered. Okay, yeah, 10 answers, and most of them said x equal to 0, and some of them said any x that is sufficiently close to 0. Okay, yeah, let's have a look. So what do we have? We have here Let me plot here the time. What was it? I think it was k, the time index, and here we plot x. So let's say this is 2. This would be the upper limit of the allowed interval. This is -2. This would be the lower limit. And let's first have a look at the case which no one chose, x equal to 2. Say we are here. So if we do not do anything, the state would double. So after one time step, so in this case, we would really go out to x to 4. So we have to counteract with at least u equal -2 to stay inside, right? And this means that we'll create a cost of 2 squared, so it's a cost of 4. That's quite high. 0 is fantastic, because if we are at 0, after one step, we stay at 0. And we don't have to control anything. So we have no control effort, so control would be 0. That's much cheaper. And what about sufficiently small? Yeah, okay, that's okay. So for example, if we start here, then after one step, it will double. So we will still be inside without doing anything. So for one step, this would also be a perfectly good answer. But if you think about more than one step, if we are here, we stay here, right? So nothing to do. If we are here, and after, I don't know how many, depends on where we start, but after a finite couple of steps, we will start, at some point we have to counteract, because otherwise it will move out, which we don't want. Right? So x equal to 0 is the correct answer if you consider several steps into the future. This one would be okay if you consider one or very few steps into the future. But so what do we expect then from our optimal control problem? Well, we probably expect that it does something like that. It goes to 0, and here's the optimal trajectory for n equal to 5, starting in 1.5, so somewhere here. And you see what the optimal control does. It actually first goes a little bit in the direction of 0. 0 is here, but not too far. At this point, it decides that it's actually cheaper just to put so much control effort that at the end we exactly maintain the constraint, but not more. But that's clear, right? Why go further down if it's cheaper to just let loose and stay? We still stay inside, right? We stay feasible, that's what we want. But now let's see what happens if we increase n. So I'm not increasing it in steps of 2. So if we have n equal to 7, well, same qualitative behavior, but we go further down. 9, 11, and so on. And you see, we always have this strange arc structure where we go up in the end. But in between, we spend more and more time near the equilibrium. And this is precisely the Turnbull property. Right? So the Turnbull property says optimal solutions stay close to an equilibrium most of the time. And this is exactly what we see here. Yeah, here's another example, a macroeconomic model, one of these models from the 1970s that were very popular at that time. It's a bit similar to the one, but simpler to the one that I showed you on Wednesday. So what we do is we want to have this dynamics and this cost function, and we want to minimize this finite horizon objective. So what are the variables here? So x is invested capital, and then by this equation you see immediately that u is then the investment in the next time step, right? A times x to the power of alpha is the capital that you get after one time step, so it's more than you had before. A and alpha are chosen so that this is larger than x itself, so your capital increases because you make some money by investing. And then this a x to the power of alpha minus u is the capital that you have after one time step minus the capital you reinvest. So this is what you can consume. And this logarithm is the typical concave utility function for which quantifies the benefit of consumption. We want to maximize that, and since we are always minimizing it, this cause of minus. So we want to kind of maximize the benefit from consumption in this model. So it's a kind of model that tries to find out the optimal compromise between investing and consumption, right? So what do we invest for the future and what do we consume now? And actually, you can compute that on infinite horizon. It's actually optimal to stay at this equilibrium. This will, if you really do it infinitely long, this will give you the best compromise between both. And what happens if we do it on finite horizon? So this is blue line is this equilibrium here, the infinite horizon equilibrium, and the optimal trajectory for n equal to 5 is the following. So we have to start with an initial capital of 5 units, whatever the currency here is. And of course, in the end, we have to spend everything because the optimization objective just rewards you for spending money, not for keeping money in the future at the end. So at the end, it will always be 0 because you have to spend everything. But the way how you do it now changes if I increase the horizon again. You see that between the initial time, the initial capital, and spending everything, the optimal solution spends more and more time at this infinite horizon optimal equilibrium, right? So we somehow the finite horizon problem is very similar to the infinite horizon problem because it stays here most of the time, right? Okay, so that's another example. Another example for the Turnpike property. And now the question is how do we formalize that? And there are again many different ways, and I'm giving you just one. So what we do is, so one way of formalizing that is we take a neighborhood of the equilibrium, an arbitrary neighborhood, this maybe this blue one, and then we count the number of points where the solutions are not in this neighborhood. And if you do this counting here, you see it's never more than 8. So it's 1, 2, 3, 4, 5, 6, 7, 8. If we count this as inside, and no matter on which trajectory you look, it's never more than 8 points outside. And then the Turnpike property requires that the number of points outside the blue neighborhood is bounded by a number which is independent of n, and here it's 8. And of course, the number depends on the size of this blue neighborhood, right? If you make it smaller, then there will be more exceptional points. But the important thing is that we find a bound that is independent of n. That's the important thing. And of course, the bound will also depend on the initial condition. If I start much further away, then of course we will have more exceptional points before we reach the neighborhood. In continuous time, you can do the same when you would use the Ledeck measure rather than just counting points. Yeah, that's how you formalize it. And a little bit of history. This is a really old property. It was observed first by Ramsey and von Neumann, all in economic context, actually. The name Turnpike property was coined by Dorfman, Samuelson, and Solow. So originally, a turnpike is this kind of thing, so a moving barrier that you can move up and down. So it's a pike, some long stick that you can turn. That's where the name comes from. But it has then been used actually as a name for highways, of toll roads actually, in the northeastern part of the US in particular, like the Massachusetts Turnpike here, because they were originally blocked by such a turnpike. So this is how the name carried over. And if you look at this turnpike property here in this example, what Dorfman, Samuelson, and Solow observed is that the turnpike is like driving on a highway, right? So if you want to go from here to here in the best possible way, what you do is you go to the next highway, you enter the highway, stay on the highway until convenient to leave. So it's essentially a highway property, what they said. And the equilibrium here is precisely the highway where you can go fastest, or in this case, make the most profit or whatever, right? Or be cheapest in keeping the system inside. So it's the best possible point. Was studied a lot in the 1970s. It has received renewed interest since about 10 years. So 2015, it more or less started. It really took off. And there were different communities interested in that, PDE optimization communities, because you have the same if you want to control PDEs optimally. There's model-predictive control, and I will tell you about that. But there's also topics like learning in neural ODEs, where Turnpike property has recently turned out to be very influential. And I'm not sure whether Enriquez will say something about that when he's here later this month, but he worked on that too. And yeah, my topic, of course, is model predictive control, and I will explain this in a few minutes, what this means. Before I do that, I would like to say that there's another very classical property which is very closely linked to the Turnpike property. This is what is called strict dissipativity. And this is something which at the first glance looks completely different. It's like an energy balance equation of energy balance inequality. If you consider this lambda, which is now a new quantity, it's not the co-state that we had before. If you consider this lambda function, which is called a storage function up here, if you consider that as a quant measure for some energy that is in the system, then what this inequality tells you is that the energy after one step is less or equal than the energy we had before, plus something, which is this term here, which is supplied from the outside, supplied or extracted, plus some dissipation term. So this alpha term here is always negative unless we are in equilibrium. So this alpha function would be the function that is 0 and 0 and then increasing. So this function is negative unless the x is equal to the equilibrium. So it's some kind of, you can see there's some kind of energy dissipation, but of course in many applications it doesn't have to do anything with energy. It could also be like profit or capital or any other quantity. But it comes originally from physical energy considerations. And the facts are that strict dissipativity implies the Turnpike property, that if we have a controllability condition on our system, it's actually equivalent to a robust version of the Turnpike property. Robust here means we do not only see the Turnpike property for the optimal solutions, but also for near optimal solutions, which are optimal up to some epsilon, right? That's the robust version. And it's really, if we have the Turnpike property, we know that there exists such a lambda, and conversely, if there exists such a lambda, then we have the Turnpike property. This is a bit analogous to asymptotic stability existence of a Lyapunov function, right? So that's the analogy here. And this means that whenever you are assuming the Turnpike property, it's not very restrictive to also assume dissipativity or the strict dissipativity. And then you have some quantities to play with and proofs. That's really important. Proving things with the Turnpike property itself, it's not always easy because it's such a vague type of property. But here you get something you can build upon, you can do Lyapunov arguments and these kind of things, which is really okay, let me skip. Yes.
So I was interested in the quadratic and linear quadratic.
Yeah, linear quadratic problem, strict dissipativity is actually, if we have no constraints, it's really detectability. If we have state constraints, then it's actually a weaker version of detectability. We only require the unobservable eigenvalues to be not equal to, well, modulus 1 in discrete time or real part 0 in continuous time. So this is like a non-resonant condition, if you like. So that's how you can see it.
Thank you so much.
Yeah. Okay, yeah. Let me finish this and then we will have just a break. One predictive control in presence of the Turnpike property. This is what happens if we have the Turnpike property. This is this example again. And now we model predictive control with, in this case, n equal to 10. So each time step we look 10 steps ahead. So we optimize, we go one step, we optimize again, and you'll see that at the beginning there's almost no difference between the optimal trajectories. Right? You'll see the difference in the end, but not in the beginning. This is precisely what causes the solution to be a real good solution for the infinite horizon problem, right? So you really see goes like that. And the funny thing is now, if you always follow the first part, you will never make the so-called leading arc. You will stay at the equilibrium. And that's precisely the qualitative property that the infinite horizon optimal solution would have. So if you have the Turnpike property, then model predictive control will give you something which is qualitatively but also quantitatively really near optimal for the infinite horizon problem. And this is what I would like to state in a theorem here. So assume that we have an optimal control problem. We assume strict dissipativity. We assume some regularity on the optimal value functions, which I will not discuss here. It's some continuity assumption. And then we get three properties. We get semi-global practical asymptotic stability. We get approximate transient optimality and approximate average optimality. And since I assume that most of you have never heard about these properties before, I would like to explain the first two graphically, what this really means. So, yeah, this is time here now for n. The blue line is this optimal equilibrium, and now what happens is what we can prove is that we have a certain neighborhood, epsilon 1 of n, such that if we do model-predictive control, our solution will enter this neighborhood and then stay in there. What it does in there, we do not know. What we know is that this size of the neighborhood goes to 0 as n tends to infinity. So the longer we look into the future on each time step, the closer the solution will eventually become to the equilibrium. If you have looked closely, let me quickly go back to that example. If you have looked closely here, with n equal to 10, we are not exactly at the equilibrium. Right? We are a little bit away. We converge to something which is still steady, but it's not exactly the equilibrium. So this is precisely what we see here, that we go near the equilibrium, but not exactly there. And now the question is, what is this? This is what is called this practical asymptotic stability. Practical means as good as, right? If epsilon is small, you can't distinguish in real world problems whether you are asymptotically stable or not. And yeah, so, and what is now this transient optimality? Well, for transient optimality, we fix some time k where we are inside this neighborhood. And then we look at different possibilities to control the system from the initial condition to that neighborhood. And then the statement is that what model predictive control will give you is the cheapest, except for some error term which tends to 0 as n tends to infinity. So model predictive control will give you, among all trajectories that go here, will give you the cheapest one up to some error term that again goes to 0 if you let n to infinity. There's also a term depending on k here, but if you look at relative errors, this would vanish. This is for the absolute errors, nothing to really worry about. So this is yeah, the transient optimality. So model predictive control will give you something which is well asymptotically stable at the equilibrium, at least almost practical, and something which moves to the equilibrium in the cheapest possible way up to some error. So it really has optimality properties. Okay, yeah, let me stop here, and after about, say, 10 minutes break, I will go to the use case optimal start for a combined cycle power plant. One question, yes.
So example, another question. You always assume that the equilibrium state is unique. Is that always the case? We may have
no, there may be many equilibria, but there's one optimal equilibrium. Yes. So all other equilibria have higher costs. If you evaluate the cost in the equilibria, this is the cheapest one. That's what I assume, and that's implicit from. I mean, it's somehow from the turnpike. I mean, if I had an equilibrium which were cheaper, then the solution, if I start there, would stay there, not go to the not have this turnpike property. So it's implicit in the turnpike property already that this happens.
So it's optimal with respect to the objective function.
Yeah, right. So what you do is you look at all possible equilibria. So we have like x, let's call them x hat and u hat, and then you evaluate the cost there, L of x hat and u hat. And the equilibrium that where the turnpike occurs is the cheapest of all of these, where you just look at the function as a static function. You can find this equilibrium by solving a static optimization problem. And just for the experts, if you do that, and then you have Lagrange multipliers for the constraint that the point is in equilibrium. And if you are lucky and the problem has a good structure, then this Lagrange multiplier allows you to build a storage function for dissipativity. That's how you get the relation, at least for some problems. Okay, yeah, let's have 10 minutes break and then continue.
Yeah, this is nice. I saw this last in relation to
I have another question, sorry. I need to explain. I'm told you I'm on a competition of economics. So I always heard about Ramsey, about so those metals in infinite time. And talking about steady states area, and something that one mathematic for was not acceptable was we were considering the steady state system. So that I will continue studying.
This theory works in both continuous and discrete.
Yeah, and the thing that I couldn't accept.
Something to write also.
Something I couldn't accept was another because and start to minus and so the steady state actually is a universe equal to x, right? And they will say, okay, that's the steady state with the in this case I think 0 and going down if you is equal to 0, let's see minus 0 and that's also 0. So let's equal to 0 is the steady state. But I will say no. I think that's the turnpike theorem enters here. And this will say, okay, that's really so x equal to 0, x equal to 0 is steady state. But and it's also stable because I have negative high values. For me, there is the condition. This is quite a strange because my system will never unless it starts. So they are saying let's get rid of the transient and so let's expect that and this and the system starts from there. And then I'm sure that going on this will be my equilibrium control. And they always do that. And when I ask many times we all around the world, from special, they told me, but can you explain me why? Every always said Ramsey did, and so but perhaps it's the term right. Yes, I know. It's about the linear quadratic because and so I really wanted to go that's my answer.
And it's quite the same. It's not so nice, but it's enough. Minimize, it's not to minimize concave, then you can always find the storage. Precisely what I explained. So you, so drop me an email, then I can send you some papers. Also, the link I can write the
okay, the second question is, do you know Peter Grasso? Yes. That's the one, and I invite next December And I wanted to implement to explain the numerical methods of use MATLAB and the package. And so perhaps this here because this and not it's not PhD, but I simply want to know how I might see the difference in and yes, I was really but I was wondering, of course, you should have done it. But it's anyone who wants to control those from the I will set up a project. Gustav is a friend of mine. It's my office for lack of everybody. Especially you. Okay. No, it's okay, so thank you. I'm sorry in our last die. And so, hopefully, yes, was fees, trunk fees, going to and you know,
No, yes, I think
Okay, so let us start again. Yeah, I would like to show you a little bit what you can do with model predictive control. And this is a collaboration with Siemens Energy in Germany. They are running big, what is called combined cycle power plants. And these are really huge things. This is one of these in Austria. These are plants that generate electrical energy via a combination of gas and steam turbines. So the rough idea is that you first have the gas turbine, where the gas goes, the burned gas goes into, but then the exhaust gas, which is still very hot, that comes from the gas turbine, produces steam, and the steam then goes into the steam turbine. So you actually drive two turbines by one combustion process. And that's a very efficient way of extracting the energy from the gas. So here it's a scheme how this is done. So you have the gas turbine, then the exhaust gas, the hot exhaust gas from the gas turbine goes into this steam generator. The steam generator produces steam. You have some high pressure pipes, and then this goes into a steam generator that runs here, and then this is a so-called single shaft model where they both turbines drive the same generator, and there's a clutch that decides whether this will be connected or not, right? So this is the we have a paper on that you can also download, so that the picture is also inside. Yeah, so that's the basic scheme. And they can actually reach up to 64% efficiency. So 64% of the energy that's in the gas can be converted into electrical energy. And if you use the remaining heat, say for a district heating system, you can do even more. But even the 64% are really well. That's really state of the art at the moment. Now, as you might know, Germany is more and more turning into renewable powers, and this is of course not renewable power, but it's a very common belief, and I also share that we will need these gas power plants for many years still to cover those periods where there is not enough solar and not enough wind energy. So it's like dark periods in winter where there's little wind. So and for this purpose, they must become very flexible. So you have to be able to start them up very quickly. If you know that there is like a shortage of electrical energy, you have to be able to start them up. And that's the task of this project. We want to develop control strategies for flexible, fast, and also economic startup. So the objective is we want to reach a desired load level, so the load level where we then can connect the plant to the grid with minimal fuel consumption. And this is like the typical what is called an economic MPC problem. That's the kind of model predictive control problems I have talked about so far. There's a practical constraint, which is that the electricity is, at least in Germany, and I think it's throughout Europe, is traded one day ahead. So essentially all the companies that run these big plants, they have to provide a plan one day ahead how much electricity they are going to produce. So this means that the optimal reference is usually computed in advance and tracked by model predictive control. This is somehow a little bit contradictory to this idea that we want to start up quickly if needed. So essentially we fulfill both purposes, but in a sense, what is done here at the moment is that the optimal startup trajectory is computed in advance, and then MPC is just used to make sure that we follow this trajectory. Okay, The interesting part is there are a lot of constraints. So it's really a constraint optimization. We want to ensure safe plant operation. So too high pressures in all these pipes must, of course, be avoided. There is a lot of low-level control going on, right? So each component has its own little control system, which is not optimal control, but just classical like PID controllers. And the MPC that is somehow on a higher level of hierarchy has to anticipate what's going on below in order not to give commands that are not admissible or contradict what the underlying systems would do. The most important constraint in this project is to avoid what is called excessive wear and tear, because if the steam temperatures, when powering up the plant, if they rise much faster than the wall temperatures of the pipes where the steam goes through, then we get high temperature gradients in the walls of the pipes. And this causes thermal stress, and this is what mostly should be limited here, right? So you should heat up constantly, but not too fast and not with too much like steep gradients to minimize this thermal stress. There are several measures that one has here to avoid these high temperature gradients. You can inject water to cool down the steam if necessary, or you can just ramp up the gas turbine in a slower mode. Both is not really what we want, because injection of water to cool down the steam means that we are essentially wasting energy, and this is somehow is against the flexibility that we want. We want it to be fast, right? So both methods can be used, but they should be used with care here. There's of course a big model behind. The model is derived from conservation of mass. I'm going quickly through this because I'm not allowed to show the details and the constants and anything anyway. That's of course company property. But there's of course some conservation of mass in the steam circulation there. There is conservation of energy, where we have all these heat transfer also going on. There is convective and conductive heat transfer. So convective heat transfer is the heat transfer between the steam and the wall of the pipes. And particularly for the model, interesting is the conductive heat transfer that's inside the wall material of the pipes, because this makes everything a partial differential equation here. So we have a partial derivative here with respect to the cross-sectional area. So you have this pipe, so you from say inner to outer part of the wall. This is what this X would measure. And we have kinetic energy, we have the work performed, and everything comes together into a huge partial differential equation model with a lot of algebraic constraints. And they were actually able to reduce this to a model that is good enough for doing model predictive control, which has only 30 differential states and then 300 algebraic constraints and 430 constraints, which is amazing that they were able to do that. So they have a very big model running on a simulator, and they have a small model that they use for the optimization step in the predictive controller. That's really amazing that this works, but still for dynamic programming, 30 differential states is way beyond what you could do. So there's no chance to do that. The optimization objective is an infinite horizon objective. You could do it with a long enough finite horizon, which is a bit of it's a bit of cheating here. So phi of t is the fuel consumption at time t. So we want to minimize the fuel consumption, but only until we reach this point where we can connect the plant to the grid, because then they switch to a different controller that would control the set point where they want to run it. So this is what this mu does. So mu is equal to 1 if the desired load level is not yet reached, and 0 otherwise. So there's no cost anymore once we reach the load level. Okay. So and now we would like to use the turnpike property. And yes.
You do not put any information on the time. You don't want a short time to get.
Well, they actually tried different things. They also tried time optimal, but what customers really want is the cheapest way, and that's also in a sense the most ecological way. So burn as little fuel as possible to reach the
this may imply that you are normally
we will see that it's not the case. That's what they found out, right? So they tried this in simulations and they found out that the side effect of this is that it's actually also quite fast. You will see the experimental results. Yeah, so turnpike. Well, turnpike means, well, we have this turnpike property, and the rule of thumb is that somehow the prediction horizon should be long enough so that the optimizer can find the way to the turnpike, right? So if the prediction horizon is too short, so that the optimizer cannot see in a way that it is optimal to go to the equilibrium, then we will not get something that will give us infinite horizon, near optimal infinite horizon solution. And what they found out is that in order to reach the turnpike for this problem, the prediction horizon, simulation time that is, must be about 1 hour. And 1 hour means that we get optimization times, if we optimize that are far too long for an online implementation. So they have like sampling times which are several seconds. So it's not really quick, right? Because it's a slow system. But it's not possible to solve this optimization problem in each MPC step if you solve it directly. And so even if there's not this day-ahead reference desired, which I talked about before for legal reasons, it's really beneficial to first compute the optimal startup trajectory in advance, and then track it by what is called tracking MPC, where the objective is just minimize the distance to the pre-computed trajectory, right? So you just want to stay close, and that's the objective. And for tracking MPC, you see immediately that the reference trajectory that you would like to stay close to is the turnpike. That's it's not an equilibrium, it's then the time-varying turnpike, but the same theory applies. And then if the system state is not too far away from the reference, and it turns out that the prediction horizon in simulation of a few minutes is suitable, and that is perfectly online feasible. Yes?
The reference trajectory is computed in advance?
Yeah. The reference trajectory is computed in advance, again using optimal control. So it's the trajectory that minimizes the objective that I have shown you before. It's computed by optimal, maybe even by predictive control, but with a longer horizon, it takes longer. And then what you do online is you just minimize in your MPC scheme the distance to this pre-computed optimal trajectory. But now, of course, there's a problem. In the online phase, you do not really know the initial state of your plant, right? So it may happen that the reference trajectory is too far away from your current state, and then you have a problem. So what they really do is they compute a whole library of optimal references beforehand, and then choose the one that is closest to the current state and use that for the reference. Okay, yeah, this is I used to call this experimental results, but the colleagues by Siemens corrected me. This is not experimental. This is just how they use it now. This is implemented on several gas power plants throughout Europe already. This is really like the day-by-day business somehow. So it's not experimental, not test runs, but real runs. And what you see here in all these pictures are the dashed lines, which are several runs of conventional startup as they did it before. This was designed by some engineers, more or less by, not purely by hand, I guess, but based on experience. And the solid lines are the non-predictive control runs. So these are these ones here. And the black one is the reference that was computed beforehand that we would like to follow. What you see here is the power that is produced. So you see that the power is ramped up, and there's a certain point where the power remains constant. And this is, I guess, this second ramp up happens when the steam turbine is turned on, right? And then you get another increase in power, and this is where startup is turned off, and then you switch to the other controller that governs the regular running. And you see that with this fuel optimal, we also gain a lot of time. So it's about 2/3 only of the startup time that we had before. What's the secret? What is the optimal controller doing differently than the, okay, this is the amount of burned fuel. You see that fuel is actually, at each time, the fuel of the optimal strategy is not lower than the fuel at the previous strategy. But since it's shorter, the overall fuel in the end is, of course, lower, right? If we integrate over that, because we end up earlier, we also need much less fuel for powering up. Yeah, what's the secret? This is the so-called HP bypass valve. This is the valve that decides how many steam goes to the steam turbine, into the steam circle, which eventually is needed to be powered up. And the bypass means when the valve is open, then the steam goes just, I don't know where, to the outside or whatever, so not into the system. If the steam is closed, it goes to the system. So the lower the value is, the more steam goes into the pipes. And what you see is that the optimal strategy, they put right from the beginning much more steam into the pipe. So it starts the heating up process much earlier, while the conventional strategy would open this valve, well, let the steam go out, and only from this point on really starts to heat up the pipe. So heating up the pipe starts much earlier here. And this was somehow the insight that was obtained from the predictive controller and from the optimal controller, that this is possible. Seems quite natural to me, but I don't know why they didn't do it before. But you see that this is really the secret. And yeah, here you see when this is when the steam turbine is turned on. This is what I said is about the second ramp. You see that this happens much earlier. Then they can do it much earlier. And what is really interesting is this is a measure for the temperature stress in one point on the pipes. And you see that the MPC strategy actually has much less temperature stress than the previous strategy. So it's not only faster and cheaper and more economically friendly because we burn less fuel, but it's also, well, more gentle to the pipes, right? So the thermal stress is lower. So it's really a success story, and that's why they implement it now throughout most of them. So their plan is, I think, to roll it out to all their customers as soon as possible. So it's really something that worked very well. Okay, yeah, let me quickly summarize this part 4. So I explained what model predictive control is, and in a sense, you can say it synthesizes closed-loop solutions from open-loop controls that are open-loop control problems that are solved iteratively. Generates the feedback law then by online optimization, not by computing a map or a closed-loop expression, but by online optimization. We can prove near optimal performance if we have turnpike property and dissipativity, and it's really highly successful in industrial applications. And one example was that. But there are also much smaller things, like in car engines. It's now used. It's used also for hybrid cars, for example, to decide when to turn on the electric motor and when the combustion motor, and all these kind of things. So you have some. It's not on the lowest level, right, in control system, but on a slightly higher level where some planning is involved, it's really something that is used very, very frequently. Okay, the last thing, maybe a bit less than half an hour, I would like to talk about reinforcement learning again. I have already explained to you how this works in principle, that you use deep neural networks for storing the optimal value function. And the question that remained, and we already had this brief discussion after your question on Wednesday, I guess, is, well, do we really gain something? And how much neurons do we need in the first place to get a faithful representation of an optimal value function, right? So that's the question here. And this is what I would like to explain here. So I would like to identify structural properties of optimal control problems under which deep neural networks can indeed avoid the Kurzmacher-dimensionality. So not only it may be, but I want a precise mathematical statement here. And what we do there is we use ideas from distributed optimal control to describe these properties. And I would also like to give rigorous estimates for the approximation error. This would be, yeah, the last result I'm going to show. That's the outline. I will briefly remind you from Wednesday what deep reinforcement learning is. I will then talk about a certain class of functions, separable functions that can be very well approximated by deep neural networks. I will then talk a little bit about distributed optimal control, and then these things come together by using something which is called decaying sensitivity that I will explain in the end. Okay, brief reminder, what was deep reinforcement learning? It's all about this optimal value function. I'm only talking about infinite horizon problems now, just for simplicity. You could also do finite horizon, but it gets a bit more messy because of the time dependence then. And what I said is once we have computed this object, we can easily get the optimal feedback from that. So this is what we would like to compute. And I'm talking about only V now, not Q. You could do similar things for Q also, but I'm leaving that out. So, and what you do in deep reinforcement learning, you use deep neural networks for storing the optimal value function in the hope that you can store good approximations also for high-dimensional state X, right? Which you can't with the okay. And as I said, you can do the same for Q, but I'm not going into detail. Okay, I already explained deep neural networks. This is essentially the same that I explained before, just rotated by 90 degrees. So the input is now here on this layer. Here we add each block here is a scalar value. We input our state vector x1 to x. Here it's called b, but drn should be the same. We process this during the network and we get some output value, which is in this case called w, and this should approximate the optimal value function for the state that I put in here. What happens inside? We have here, in this case, two called hidden layers. In the first hidden layer, we take the input, multiply it with the weight vector. This is the scalar product here, the dot. Add some bias term, plug this into a nonlinear function, and the weights here depend on k. So each of these hidden neurons, as they are called, they have a different set of weights. And then we do the same on the second level. Here we don't take the input values, but we take the values from the previous layer, process them in the same way, put weight, multiply with weights, add a bias term, add a nonlinear function, and then do it here. And then in the very end, we do essentially the same here, except that we do not use a nonlinear function. It's just a linear combination plus some constant term. Yeah, so the W's are called W's at the A form, they are called vectors. The B are scalar parameters, usually called bias terms. The sigmas here are called activation functions, and I already showed you some possibilities. So we had these three, I guess I already showed you on Wednesday. This is the simplest one, it would be the identity, can sometimes also be used. Yeah, all the parameters that we have that we want to determine are put into a vector called theta. And then we would like to find theta star so that the W represented by the network is close to V. That's the idea, right? So the problem is determine all these weights and bias terms that are up there so that we get a good approximation of V. And yeah, so the network is essentially trained such that we either satisfy the Hamilton-Jacobi-Bellman equation or the Bellman equation as good as possible. How exactly this is done, I explained a little bit on Wednesday already, so I'm not going to repeat that. But that's the idea, that we would like to get an approximation of this equation, and then by using usual results from the stability of the solutions, we can conclude that we have something that is really an approximation to the optimal value function. So training, I will not discuss again. We had a little bit of that on Wednesday. So what I would like to discuss now is the following, which is kind of a necessary property, which you have to look at before you try even to train your network. Can your network represent an approximation? So can deep neural networks provide approximations here in some, where this of course must be, well, set in some norm, right? Some norm on the function space for large space dimensions, P or N. Yeah, so, and if you do that, you sooner or later will hit what is called the universal approximation theorem, because this is the class of results mostly developed in the 1990s, but also some recent developments that explain what kind of functions neural networks can actually express, right? And here the setting is we are looking on some compact set minus kappa kappa to the power of and I'm mixing D and N, unfortunately, here. So N and D should be the same. It's all the space dimension, right? I have an N here and D there. I tried to adapt the slides, but I didn't fully succeed, it seems. Okay, so the dimension is varying, and we look at the infinity norm, the usual one of V, and we look at this class of functions, we're making the assumption that V is continuously differentiable here, knowing that this is not always true for optimal value functions, but for this part of the talk, I will assume that. You can do something if it's not the case, but it's much more messy. So let's assume that. And we assume that the sum over all directional derivatives of the function is less or equal to 1. And the 1 is, of course, could be replaced by any other constant. And then the universal approximation theorem, this is like a blend of 3 of these theorems that appeared from the late 80s until a couple of years ago, says if we have a neural network with 1 hidden layer, so we saw 2 before, we need just 1, and the sigma 1 should be a function which is infinitely differentiable and not a polynomial, then for any epsilon greater than 0, there exists a network structure which provides the following approximation. I give an arbitrary V from that space up here. We can always find a theta such that the network approximates this V in the infinity norm up to some epsilon accuracy. Okay, that's the statement. And this is essentially this theorem here from Cybenko from 89. And what Maska did later on, he also checked how much, in the worst case, how much neurons would you need to get that? How large does this layer need to be? And he determined that the number of neurons, capital N here, is in the order of epsilon to the minus n, where n is the state dimension. Yeah, and now the question is, I have another quiz here, so please take out your mobile phones. So assume that we have exactly this property, so that we need O of epsilon to the power of minus n. So if we now want to reduce the accuracy from epsilon to epsilon over 5, how much more neurons do we need? Do we need to increase the neurons by a factor of 5, by n to the power of 5, or by 5 to the power of n? What do you think? It's not too difficult, actually. You have to think a little bit. Anyone done who wants to answer?
I see some still on mobile phones. Okay, let's have a look. Okay, some say by a factor of 5, some say by a factor of 5 to the power of n, and the left is more. Okay,
okay, I also have n to the power of 5 now.
5 to the power of n. Okay, it still goes, still moves. Yeah, 5 to the power of n is correct.
So the majority has the correct answer. You see it if you divide epsilon by 5, you get 1 over 5 to the power of minus n here, and then of course if you take the 5 to minus will cancel out, so then you get 5 to the power of n. And the unfortunate answer is, or the consequence of that, this is the worst of the 3, right? Because if n is large and large, so the question is what is worse? If n is large and say 10 would already be large, then 5 to the power of 10 is about 10 to the 7, a little bit less, but not much. While n to the power of 5 is obviously 10 to the power of 5, and this is already by 2 orders of magnitude larger. And the larger n becomes, this grows much, much bigger than that. Effectively, what we have is, we still have exponential growth. So for general functions, we do not gain anything by neural networks. That's the message. That's really important, and you shouldn't keep telling other people this if they claim that neural networks are, or they can be because of dimensionality. No, that can't be true. We still have exponential growth in the number of neurons unless we have certain properties, unless we have certain classes of functions, and separable functions are the functions I would like to discuss here. There are other ways to do that, but separable functions turned out to be very useful for these applications that I had in mind, so I'm going to use that. What's a separable function? A separable function, and I'm writing this here in terms of the Z, is a function that is a sum of lower dimensional functions. So each of these functions, Vj, now depends on the vector Wj, and Wj is a subvector of our big vector x here, which contains at most Dj elements, right? Or exactly Dj elements. So it's really like a low dimensional subvector. what we can then do is we can approximate, we can build a neural network that approximates the individual J by this boxing. And if the number of these blocks grows then only linearly with the dimension, and if we assume that the dimension of the subvectors is constant compared to the overall dimension, then what we get is we can apply the universal approximation theorem separately in each gray block. And what we get is the following theorem, that these functions, where this dj is bounded by some dmax independent of the overall dimension, they can be approximated on the set K with any accuracy with a number of neurons growing only polynomially in D. Yeah, more precisely, we can even say how much this number of required neurons is. So we have epsilon to the power of minus d max. So it's actually d max, the dimension, the maximum dimension of one of these subvectors that determines this. And then we have another term here which depends on d. And you see that we do not have d in the exponent, but we have d in the base of the exponential. So it's really a polynomial. So that's the statement, and that's much slower, much slower growth than what we had before. But of course, we need this special structure. And now the question is there other optimal control problems where the optimal value function has this special structure? And yeah, this distributed control leads the way to get that. So what we assume is that we can decompose our system into S subsystems, and they depend on subsets of the state vector. So we write the state vector here. So Zi is the state vector of the I subsystem, and the vector field that determines that depends on Zi itself and on Z minus I, which is all the rest, right? And each subsystem has its own control input. That's important for the structure for this kind of thing.
Oh, sorry.
Yes.
Does it mean that it doesn't exist any multiplicative term between the variables?
No. It can be any relation. What I'm doing at the moment is just I just decompose my big vector into small vectors Z1, Z2, Z3, right? So that's so these are the subvectors, and here it's not at all determined how they interact. They can be additive, they can be multiplicative. So it's at the moment it is just writing. You can do this with every system. But the question is, do we get anything out of it? And this is the next part. The next part is we now express the interconnection via a graph. And this tells me which variable appears where. So let me explain this. Whenever Fi depends on Zj, then we have an edge here. So formally, this Z minus I contains all the other Zs, but in practice, not all of them may appear here. Whether they appear multiplicatively or additively doesn't play a role. The question is, do they appear or don't they appear?
If they are coupled or
yeah. So for example, if there's a link from Z2 to Z1, this means that Z1 would appear in the equation F in the vector field F1, or the other way around. Right? So I'm not using a directed graph here. One or the other. Right? So whenever Zj appears in Fi, then there must be an edge. And then what we can do is we can define something like a graph distance. So we can measure how many hops we need at least to go from one to the other. So for example, for node 1, from node 1 to node 11, so node 1 is here, node 11 is down there. It's 1, 2, 3, 4 hops at least. So they have a graph distance too. 2 to 6, here's 2, there is 6, it's 1, 2. And it's always the shortest, right? This one would be 4, but it's always the shortest. So the shortest path. Okay. Yeah. And likewise, we have could have a coupling in the cos, right? You have this cos L, Lagrange term in the integral cos, and whenever Zj appears in Zi, then we also have a link in the graph. So the graph structure is determined by the Fi and the Li. Whenever there is a connection, no matter whether it's here or there, we have this edge in the graph. Okay. The question is now,
how does the state of a subsystem influence the optimal trajectory of another subsystem which is far away in the graph distance? So if they are only connected via many intermediate systems. And this is what leads us to the decaying sensitivity. And I would like to start with an example here. That's a convoy of vehicles, say trucks. And we would, what is known is that if you control them and each of them tries to keep a distance from the car before, then it may happen that if you have a perturbation in the first vehicle, so say this guy has to brake, then it may really amplify. So it's a very nice student exercise. You can write down the differential equations easily, and they should determine some rule how a car should behave. And mostly, if they write down some rule, it will end up in something unstable. So a little break here will actually make this one break more, and then it's like this, how you call it, like an accordion effect in this. And you can see this in simulations. However, if we use an optimal control, then as you will see, the perturbation will actually decrease quickly. And you can do this with something as simple as a linear quadratic problem, which we can also solve efficiently. So I can really show you exact solutions now. So each vehicle is just this double integrator here. So this is the same model I had several times already. So the position, the derivative of position is velocity, derivative of velocity is the acceleration. And now there are many of them. And I would like to compute a control that minimizes the following. Functional consists of 3 types of terms. So the first is like a reference for the first vehicle, where this one should be. So it's like the distance to this reference should be minimized. This is given from the outside. The second term penalizes the distance. So whenever the distance between two cars is not capital L, this is a positive term. When they have the right distance, capital L, this will vanish. And these are some regularization terms to make sure that all the matrices that we write them down are positive definite, so that we can apply the Cartier theory to solve the problem. But these, if you choose gamma and delta small, they will only mildly influence this. So these are the terms. And what I'm showing you is the optimal solution for 100 vehicles, but I only show you the first 5 here. For simplicity, I have set all the references to 0. That doesn't really matter because it's a linear problem, whether we look at the arrow system or true system. And so these are the positions where the car should be. So capital L is equal to 1. Here, this is where the first car should be. This is where the second, the third, fourth, and so on. And what happens here now is we have now a perturbation. So the first car had to do some braking maneuver, and we switch on the control when it's actually way too close to the second car. Right? And what happens is the second car brakes, but not that much. Right? It brakes a little bit because it sees that this one is already going to recover and go back to its original position. The third one also brakes, and so on. You see that this perturbation really fades out through the graph. Right? So it gets less and less. The sensitivity decays actually with the distance from the perturbation. The question is that a particular feature of this example, or is this something general? And there is a recent paper, not by us, but by another group, that really very nicely shows it's not, it's systematic. So let's look at linear quadratic optimal control problems. So we have linear dynamics here, quadratic costs. And then the optimal value function is known also to be quadratic, so it's an x transpose tx. And the optimal control as a feedback law is known to be a linear feedback. This is known from the Cartier theory since the 1960s. And the theorem says that if we have suitable uniform stabilizability detectability assumption satisfied, then this inequality holds. So what is rho? Rho is a constant between 0 and 1 that you can compute from several constants that come out of these conditions here. C is a constant that you can also compute. dg is the graph distance. And kij is the block in the feedback law that maps the state of the jth system to the control of the ith system. And it says that the influence of Zj on ui decreases exponentially fast if the graph distance increases. Right? So we have this constant between 0 and 1. So if Vg gets larger, this decreases exponentially fast. So the further two subsystems are apart from each other, the less is the influence of that guy on that guy. It's very natural, but this exponential decay is something I wouldn't have expected necessarily. It's proved in discrete time. I think there is now a continuous time paper. This is a little bit older, but at least, but we have done this in one paper. We have done the continuous time case in well, simplified problem, but yeah, I don't think that's a real problem. And a corollary that we had, that at least on suitable graphs, which are a little bit restricted, but not too much, we also know that the block Pij of this P matrix up here satisfies the same inequality, which essentially says how much are the state of system I and system J multiplicatively connected. Right? This is really the multiplicative connection, but in the value function, not in the dynamics. And this also fades out. This is what we call exponentially decaying sensitivity. And yeah, by this, what we can do is we can construct now separable approximations. So the idea is that we would like to approximate the optimal value function by a function that is a sum of low-dimensional functions. And we now call them psi L. K is just the running index, so it's the function psi 1 up to psi s. And L says how many states of neighboring systems we've looked at inside. This would be the WK that we had before, right? This vector on which low-dimensional functions appear. Yeah, and then each WK has this dimension, and the complexity theorem applies if the dimension of the subsystem and the number L here is bounded independent of L, and then we can actually approximate this by polynomially growing neural networks. And I should mention that two natural choices, so for example, that you can write an optimal value function as an exact sum of low-dimensional functions, but also that you can use just one subsystem state here as an argument. Both will in general not be satisfied. So you need to do some approximation. You will not get this exact representation because everything is connected to everything, but only very weakly. But still, exact identity cannot be expected. And also, you have to take into account at least some near neighbors, right? You can't write down functions that only depend on the state of the individual systems. You have to, a little bit neighbor information you need to get an approx. Okay, how do we do that? Let's for a moment consider just graphs that are simple like that, where the graph distance is just the distance or the difference between the indices. That's in the convoy, right? When we have like graph things go behind each other. And then this decay of this Pj matrix here, these blocks, Pij matrix, these blocks implies that this difference here is almost the same as that difference. What is different between the first and the last? Well, here you have taken the last, everything that comes after k plus L in the variables here and set it to 0. And same here. Right? This is the difference. So we kind of remove everything which is further away than graph distance L from K. And then what we can do is we can write something, we can define this as psi LK and write some kind of telescopic sum. Right? And from this you get that the x is actually approximately equal to the 0 plus these kind of things. Because if you write the sum, then they all, and then you do the approximation, and then you get some telescopic sum where everything cancels out in the end. Right? Because here you have always one variable less. It takes a little while to digest, and but it's actually once you write it down, it's quite easy to see, but you need to cost to really plug in the definition. And the theorem says if we have exponentially decaying sensitivity, then we know what is the error between the x and this approximation. It's bounded by c times rho. Rho is the same rho as before, to the power of L, and L is precisely the number of variables that we plug here into this. So how many neighboring states we take into account. Yeah, and if we do not have this very simple graph structure, then we also need to take into account the
how much neighbors we have in the graph. So in this simple graph, every truck has just 2 neighbors, right? But it could be a graph where, say, a truck where the number of neighbors is larger, and then the number of neighbors mustn't grow too fast, right? It must grow slower than rho to the power of L. So it could be that in a tree, you would have like 2 neighbors, 4 neighbors, in a binary tree, 8 neighbors. It would be exponential growth. That would still be okay if this rho is less than 1/2, but otherwise you need to have slower growth. So they have to balance the number of neighbors that influence your system and this decay parameter here, if you do that. Okay. Now, last theoretical slide before I show a couple of final examples. For nonlinear problems, the optimal value function is, of course, not of this. So the question is, what do we do then? What is the right condition for the optimal value function so that this still works? What you actually do is you look at this difference again, and you look at the Lipschitz constant of this map,
that J maps to this difference.
You can also express this via the hash actually, if the function should be twice continuously differentiable. If it's not, then you can put it directly in this form. And then the theorem says that if the Lipschitz constant satisfies this inequality, which is precisely the generalization of what the linear quadratic thing does, then we get the same inequality. And you're also able to get estimates for slower than exponential decaying sensitivity. This is important because in nonlinear case, it's not clear that it will decay exponentially. It may also decay only polynomially, but we can still get estimates. Then of course we will have some polynomially decaying term and not exponentially. And the important open question here, of course, is when does the Lipschitz constant of this term satisfy such an inequality? And we are currently working on that in the nonlinear case. We have some first proof now for a very particular situation, but we are trying to get closer. So what I told you by this paper by Shin and all for 2 years ago for the linear quadratic case, they really use matrix analysis in a very strong way. You can't use matrix analysis in a nonlinear case. Yeah. Trying to do cases by graph theoretical arguments where we use the graph and how information propagates the graph. And it seems that this will work, but it's not yet ready, but hopefully in a couple of months we'll have the first paper. Okay, yeah, let me show you a numerical test. First, we do something which is randomly generated. So we randomly generate A as a banded matrix, and the band structure, of course, determines how much interconnection we have between subsystems. And first, what we check is whether we really have exponential sensitivity. So we just use MATLAB to compute this PJ1 matrix, and you see it really goes nicely down on this logarithmic scale to machine accuracy, and then of course it deteriorates. So it's perfect up to machine accuracy, exponentially decaying sensitivity. One question that came up a couple of months ago when a student of mine presented this is, what about the singular values? Can't we do something like low rank approximation? That would be the standard thing that bottle reduction people would do. And interestingly enough, the singular values do not decay very quickly. So it's not a low rank structure that we have here in this P matrix. It's really a different kind of redundancy property here. It's not that you can't use like low rank approximation. Yeah. We set up the following network. We skipped the second layer that I had before because the second layer is only for determining which state should go where. Here we already know, so there was no need for that, and this makes the numerical experiment similar. So we use this network structure. We have like L equal to 10. We use here the number of neurons in each block here is 16. That turned out to be enough. We use the sigmoid activation function. And in order to avoid effects due to this incomplete learning, reinforcement learning, this exploration by this exploitation, we used here supervised learning because we wanted to check whether the network can really express the function. It's not so much about the training at this point. Yeah, and for the two-dimensional problem, we actually reach a mean square or less than 10 to the minus 3 in the test data. We have
and then checked what, just experimentally, what is the minimum
number of neurons and parameters. So number of neurons and the number of weights is not always the same. In the network, if we want to achieve this 10 to the minus 3, depending on the dimension, you see that we have a perfect linear growth,
both of the number of neurons and the number of parameters. Of course, it depends on the bandwidth here, the number of parameters that we need, but it's really
we predicted polynomial growth actually in this approximation theorem. We actually here only see linear growth. And it's still not clear to us whether our estimate is too pessimistic or whether this problem has some special property that we do not yet know why it's only linear. So theory says that it could grow
polynomially, but it actually grows linear with a dimension.
Okay, and there's another thing, last slide here I would like to mention. We could say, why do we need all this structure?
Right on the neural network that has all connections here, it would be able to represent exactly the same function.
So why do the effort and write down the separable network? Well, it turns out that the amount of training data that you need to train this thin network is much smaller.
So training goes much faster if you look at the number of training data points compared to the accuracy, right? So with much less data you can train the network, while with a fully connected network you need much more data and only of
like this is a logarithmic scale, so this is really means it's 4 times as much data that you need to get the same accuracy. Right? This is really a striking thing, and same happens if we look at the training speed. So this is the number of epochs, the number of iterations. Epochs is what iterations are called in this learning theory. So also that works much better. So it makes sense to think about what kind of function you would like to approximate, how you would like to do it. It really gives you something, and there is some theory actually quite classical called anchored decompositions, and we think that maybe there might be a relation. We are currently investigating that. The student of mine is working on that, trying to find that out. Okay, yeah, quick summary and then I'm done. So what I wanted to tell you is if you use deep neural network, and in general, this will not remove the curse of dimensionality, because also with neural networks, you will need an exponential number of parameters in the state dimension in order to represent the function. But if we know that the functions have some simplifying properties, some redundancy, this is the separable approximations, then we can actually do that. And the existence of those can be established by decaying sensitivity for the case of optimal value functions. And yeah, open questions are, for example, this nonlinear, really improving exponential, or also maybe other kinds of decays and for nonlinear problems. And analysis of the sampling efficiency. Why do we really need so much less sampling points for this neural networks? This is also something we would like to understand whether there is something systematic behind. Yeah, so with that I'm done with my course. I hope you liked it. I hope you learned a little bit. Please feel free to send me emails or ask me now if you have any additional questions. As you saw, there are a couple of typos in the slides. I will probably do this next week and put up a corrected version under the same QR code. So the QR code won't change. You can use the same one that you already have to download the corrected slides. I probably send Julia and Carlo a quick email so that you know when it is ready, someone in the course of next week. Okay, I also put a lot of literature here which I already had in between for the different parts, so you just go through, and if you want to know something in more detail, I guess you will find something there in the literature. So this is for part 4, this is the last part here. So in particular, if you want to see how really this separable approximation works, this is the frequent where this is very good. Thank you very much.
Oh, thank you, Lars. So you were able to bring us and students from the basics of optimal control to the really recent topics of your work. So
I hope so, yes.
Not easy to do this. To students, I will be recorded that the recordings and PDF will be available on the Google page of this course. And that these meetings will continue on late September, September 30, with and October 1st, with Professor Emilius as well. We're not required to learn everything of what Professor Grüne did by self-play, both from self-play. So hope to see you again. And thanks again.
You're welcome.
Not forget this.
No, thank you. Thank you.
Yeah, just a little message from your text that I understand that deep learning becomes a reason for that. So there are more answers to questions. One must understand when you use deep learning for programming, you forget from the moment that is a deep learning. And then you have a kind of reinforced learning for the value function, and imagine that you store the value function in a kind of black box that is an approximation algorithm that you call deep learning. So deep learning. Yeah. So first question. And if you don't use this black box, use another one. For example, Fourier approximation. Fourier. For example, does it still works as nice? As deep learning? It's true.
If this black box has the capability to represent it. Okay, there's one thing you have to cover this to some what is called learning these days or in passing some fixed point. We have to make sure that this is a stable process. We looked at this for spline approximation.
For example,
and have instability, so they are ways to stabilize. That might be an
okay.
that
So
you
you
have to
mean
take into
a
account.
black box may be better than another black box?
Yeah. In terms of when you learn that some black boxes may have better properties.
And you think that the deep learning black box is a good black box?
I think that for some problems, yes. Yeah. So I mean, we also now have nonlinear examples with similar dimensions, I think up to 120 or so. I'm not aware of any traditional method that you need to do. But I also have to be very careful. These methods are not very accurate. They require a lot of hearing, a lot of try and error. So I wouldn't recommend this for someone who has no idea what it's doing. Right? So you have to know what you are looking for, and you have to be able to tell good results from bad results.
Okay.
It's not yet something that you can just
I understand.
So that's our experience. When we started that 4 years ago, I thought that it's much easier because so many people.
I understand. No, I know perfectly.
But they only report the good results.
That's it.
And when you now when I talk to people and say, look, we tried that, doesn't work as well as the literature says. Are we doing something wrong? And everyone says, no, it's the same everywhere. They just don't say it.
Okay. And then one other question. The black box can be more or less accurate, for example, in terms of the number of nodes or maybe number of terms in SCX funds or whatever. Do this accurate storage impact in the reinforced learning algorithm to get the control strategy?
I guess so. I have no systematic framework. I would strongly guess that.
So you think that there is a kind of threshold or you get closer and closer as most?
Yeah. So and if the black box is bad in a way, then you may not even get as close as you would like to, because somehow, I mean, this is all based on gradients. And if the black box is bad, then also the gradients you use for the gradient descent are bad, and you may get lost far away from the true solution.
Okay, thanks a lot. That's been a very nice.
Thank you very much. Thank you very much.